This is the intro video for Calculus BC, section 3.1, and in this we're going to be discussing the existence of absolute extrema with the extreme value theorem, as well as how to find these absolute extrema. So the extreme value theorem is this. This is basically addressing the existence of extreme values. So if f of x is continuous on the interval, the closed interval, a to b, then f of x will have an absolute max and min on that closed interval from a to b. This is just addressing the existence of these extreme values. Of course, we're going to have to do a little bit of work to actually find them. This just addresses the existence. And this is actually a pretty important condition for the existence. The condition is continuity. So if a function, if we can't prove that a function is continuous, or maybe we know that it's not continuous, then we cannot guarantee the existence of absolute maxes and or mins. So if a function is continuous on a particular closed interval, then it will have an absolute max and min, and that absolute max and min will occur at either one of the endpoints of the interval or a critical point, sometimes called a critical number. I'll use those terms interchangeably. Critical points, C is a critical number or a critical point if f prime of c equals 0, or if f prime of c is undefined or does not exist. And so, as you guys know, f prime of c equals 0, that is where you have a horizontal tangent line, f prime of c being undefined. There's a number of reasons for that, one of which could be one of those sharp points or cusps. And so those are potential absolute extrema, absolute min or max. So then, critical points are where f prime is 0, does not exist. That's that familiar phrase, hopefully we remember from last chapter. Chapter 2. So now what we're going to do is look at a few graphs that kind of illustrate some of the principles of the EVT and the extreme values. So first, the graph on the upper left here, let's say that we have a graph that looks something like this, goes up and then down, and then up and down again, and something like that. So what we could say with this, first of all, that function, at least from the way that I've drawn it, appears to be continuous, and so the extreme value theorem guarantees that this function will have an absolute min and max. And so we can see here, just by looking at the graph, if this is a graph of f of x, that the max would happen right about there. So that would be the location of the absolute max. And this right here would be the location of the absolute min. We're simply judging what is the highest y value, what is the lowest y value. That's going to generate our our absolute min and lowest absolute max. So just keep in mind here that on this particular graph that I've drawn, the absolute max is actually at a critical point, and the absolute min is at an endpoint. So just to illustrate what we could have had, what we talked about before, we could have had this happen where we've got the candidates for the absolute extrema are endpoints and critical points. We can see kind of a combination there. We could have, of course, a different graph. We could have one where the endpoints kind of dominate, where the endpoints are the max and the min. So you could have an endpoint here. It could go up and have some ups and downs, and then go way up over here. So in a case like this, once again, it is continuous. So the EVT guarantees the existence of the max and the min. But in this case, the absolute min is right there at the left endpoint, and the absolute max is right there at the right endpoint. We got a bunch of critical numbers in between there. Look at all those horizontal tangent lines. Of course, there's one right here. There's a critical point. There's another critical point, another one. We got 4 critical points in there, but none of them would be the absolute highest or the absolute lowest. They could have been, but in this case, they were not. Let's take a look at a few other situations here. For example, you could have a graph that does something like this. Maybe it's parabola-like, comes up here and does something like this. We got an open circle right there, and it drops back down and gets maybe cut off right about there. So with this particular graph, it is not continuous, and so the EVT does not guarantee that we have a max or a min, because this function is not continuous. We do happen to have a min The min is right here, so we get an absolute minimum on the left endpoint. But because of the discontinuity in this particular graph, we would actually say that we do not have an absolute max. If the graph were continuous right there, then perhaps that would be the absolute max, but it's not continuous, and so we have to actually say that even though we do have an absolute min, we don't have an absolute max. And then you could have even like a crazier graph. You could have something where you've got I don't know, maybe you've got a point doing something like this, whoops, and doing this right here, and maybe you've got an endpoint and an endpoint, something like that. So once again, you look at something like this graph, and you can see that it's probably for sure piecewise, but because it's not continuous, the EVT does not guarantee anything. We can't say that there for sure is a max or a min. If we were to try to really look and decide, just based on this graph, I would say that we have neither a max or a min. There's no critical points in there. We can see there's no horizontal. I mean, I suppose it gets sort of close right in there somewhere, but I don't see anything obvious. And then because we lack the continuity on the closed interval, we don't have a max or a min even at either endpoint, and so we'd go with neither here. Okay, so a couple graphs there, hopefully illustrating what we're talking about. And here to finish this video off, I'd like to talk about how we actually find these, kind of the procedure, and then in class we'll work on finding these as well. Okay, so once we've established that a function is continuous on a closed interval, we know that the EVT tells us that we will for sure have an absolute min and max. But as far as how to do that, here's what you do. First thing I would do is I would attempt to find the critical points, the critical numbers on the interval. That, of course, is going to be where f prime equals 0 or does not exist. But we want to collect those critical numbers. Next, we want to recognize that we have endpoints. And so what we're going to do is we're going to evaluate or analyze the function that we're trying to maximize or minimize at each critical number. Being a little bit broad with this, when we get into Chapter 4, the analysis is going to be a little bit more in-depth. For now, it's not as in-depth. Once we have evaluated the function at each critical number, we're going to do the same thing. We're going to evaluate and or analyze the function at each endpoint. I usually make a table for both of these, just a little input-output table, just to keep things as organized as possible. And once you've made that table, then the lowest y value is the min, the highest y value is the max. At that point, it becomes pretty simplistic. So I hope that helps either refresh your memory or help you kind of gain a little bit of understanding here. We'll do some examples when I see you in class.